Well, hello YouTube. Now, this is a surprise even for me. I said that my last video was the last for 2016, but I got this interesting topic and I thought that I must share this with you guys. It's a great topic and I love it personally. So, well, let's say it's a Christmas miracle. And talking about Christmas, I hope that you enjoyed it. So, let's now dig into some work. Now, we are discussing here and today's topic entropy, its application, why do we need that, and what are the conditions that changes for entropy in real and ideal gas situations. So first of all, let's move on more into the definition of entropy. So here you can see that entropy actually define the thermodynamic quantity that represent the amount of unavailability of thermal energy which can be converted into mechanical energy in a given system. This is some rumbo jumbo bumble scientific terms. Let's deep into the general idea. So let us say this is one system A, this is another system B. The round blocks that you can see inside both the systems represent, may say, molecules, atoms, whatever you think is comfortable. In A, it is much more organized. Okay, randomness is very low, and for example, if I want to pinpoint this particular molecule and after time t, if I want to find where this molecule is, I can find it out. But let's move to the diagram B, and let's say this is not a perfect round. Let's say this one, I want to find the location of this molecule after a time t. It will really be hard for me to find out where this molecule is because of randomness. Now let us move to a real life situation. Let's say that you and your friend has went to a carnival which is consisting of thousands of people, and suddenly one of you get lost. It will be very hard for the other person to find the other person in such a massive amount of crowd. Whereas the same park whereas the same time, if you both have went to a park in the morning for a morning walk, jogging, it will be much easier for either of you to find one another. In simple term, it is called as the randomness in a system. That is the much more difficulty by which you can find a given molecule within a given space or a given system. Now, in the early definition, we have said that it is the unavailability of thermal energy. Yes, because we cannot easily pinpoint it in our real life situation. Similarly, understand that a particular amount of energy is always unavailable. We call them the wasteland energy. This is not a scientific term. I just tell it. It's a wasting energy. Just remember in this way. It's a waste amount of energy that cannot be converted into mechanical energy. These are thermal energy which cannot be converted into mechanical energy. Before moving into the further, I will just like to introduce a pinpoint fun fact. The entropy of our universe is always expanding. Yeah, it's always expanding. At any given instant, the entropy of our universe constantly increases because many cosmic activities take place, and some of the amount of energies always goes into waste. That energy cannot be converted into useful work. Now let us move on to application of entropy in ideal and real gas situations. Okay, now we are moving on to find the entropy of an ideal gas. I will end this video on this ideal gas only, but if you want me to continue over the real gas derivation, just mention it in the comment, because real gas derivation is a little bit more difficult and I don't think that any syllabus will contain the derivation of entropy for real gas, because real gas is much more complicated than ideal cases. Anyhow, let's move on. Let us say that for 1 mole of ideal gas, ds is equal to Cv dt by d plus R dV by V. What is this? This is from the second law of thermodynamics. What does the second law says? Let us move to direct Kelvin-Planck statement, or you can move to Clausius statement, whatever statement you like. The statement actually says that it is not possible to derive or devise actually any heat engine that can suck up any amount of heat supplied to it and can convert 100% of that into eligible work. That means at any given heat engine, a particular amount of work will always be lost every time. It is not possible to make a heat engine that can work ideally it will always lose a particular amount of energy into waste, generally heat energies that are. Here S signifies more of a entropy change, ds. Cv is the volume constant, dt by t change with respect to time, r universal gas constant, dv by v change of volume. Alright, let's move on then. Now integrating the above equation, we get S is equal to Cv specific when constant volume ln T plus R ln V plus SO. This SO is nothing but a constant of integration. Okay, now let's move on. We know that Cp minus Cv is equal to R. Okay, and we also know that PV is equal to RT. This equation is applicable only for ideal gas. So we can change it and we can write it as V is equal to RT by P. Alright, now let's put everything back into this equation and rewrite it. Once you have done everything, you will get this is the new equation. Cp ln T minus R ln P plus S dash 0 or not, whatever you say. This is same. S naught and S dash naught both are constant for integration. Now let us say that the gas is made up of several ideal gases. It's a mixture, and they are made in N1, N2, N3 plus dot 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 amount of moles are present for each gases, N number of moles. Okay, how the equation will affect, let's move and see. So if we continue and modify the equation, we will get N1 Cp ln T minus RL ln P1 plus S dash naught. P1 is again the pressure for the first gas and N1 is again the mole for the first gas. Similarly, we will get N2 plus Cp ln T minus R ln P2 S naught S dash naught. Continue, we will get N3 Cp ln T minus R ln 3 plus S dash naught. Continue this till up to N. So we can write this up as summation of N times Cp ln T minus R ln P plus S dash 0. This is what will happen for a mixture of ideal gases. Now this N can be nothing, it can be just 1, it can be, or it can be the number of, it can be many, it can be 100 gases as a mixture, 1000 gases as a mixture, doesn't matter. The equation will modify itself accordingly. Now the partial pressure of N mole of ideal gas is given by this equation. This is called Dalton's law of partial pressure. That is, the partial pressure from each gases multiply the times of its mole will give you the pressure of the total pressure. You sum it up and you get it. We will use this idea in this equation and then we'll continue. Let me write down the forward equation because it is really difficult to hold the camera and write. So let me write it down and then we'll continue. Once you input this idea into this equation, you will get S is equal to summation of N Cp ln T minus R ln P minus R ln X, this I will explain just now, plus S naught. Now what is this X? S is nothing but the mole fraction. If you go back to Dalton's law of partial pressure, just pause the video and open Google and search for Dalton's law of partial pressure. Read it out. It will clearly says that the partial pressure of a given mole of gas, just multiply the mole to it, it will be equal, and sum it up, it will equal the total pressure of that particular gas. For example, if I want to find the total pressure of our air, what I have to do? I have to find the mole fraction of nitrogen, oxygen, all other halogen gases that are present, even carbon dioxide, nitrous dioxide, sulfur dioxide, because they are present in not in pure clean air but in city polluted air they are present, and then I have to multiply that by the mole fraction of each of these gases. That particular pressure will be equal to the total pressure of air. Similarly, here X signifies the mole fraction of that particular gas, P signifies the pressure of that particular gas, and N signifies the number of mole of the particular gas. T, remember, is constant in this particular case. In the entire scenario, the system temperature will remain constant. This particular equation, S is equal to summation of N Cp ln T minus R ln P minus R ln X plus S dash 0, signifies entropy of an ideal gas. If you like it, do subscribe, leave comment, and obviously like the video, share it as much as you can, and do check our Facebook page. I have given the link in the description, and please let me in the comment that whether you want to get the derivation of entropy in real gas situation. Please mention that in a comment. I will try to make it as soon as possible. Thank you. Have a lovely new year. Bye.